Arklow Bank, which you'll see is an excellent radar aid to navigation. And that, again, is the Raycon on the Arklow buoy. Moving back to the modern Raycon on the pier at Wicklow, you can see a response there, just clear of the land clutter, at 9 miles. So we did get actually 10 miles from that Raycon on the S-band NT radar. And that was the main significant result from this trial. We then headed north for the Codling Lambdy, and this is an old type Raycon, giving a response, but at about 2.5 miles in that case. Coming into the approaches to Dublin, you can see AIS targets being picked up on the display there, but this is the Raycon of interest on the Kish Bank Lighthouse, and that was an old Raycon, which, as I said, is no longer in production, but giving a good response there, but at only about 3 miles, and maximum response was about 4.5. And finally, the Raycon on the Dublin Bay buoy, modern design, but with no special attributes, but giving a response there at about 4 miles. And you can still see the trail of the Kish response there as well. So that's a quick run through the results that we got from this trial, and as I said, the significant result was that although the NT radar did trigger most of the Raycons, but at substantially reduced range, generally less than 5 miles, the new version of one of the Raycons tested gave up to 10 miles, and that was almost certainly because of its improved receiver sensitivity. Most of the inconsistencies in the responses of the Raycons which were seen in the earlier trial were resolved, and were either attributed to power supply problems in one case and to reflected signals in others. In general, the ranges with the conventional X-band radar were better, getting generally around 10 miles in all cases. Also, the clarity of response was much better, except at close ranges where the X-band tended to get lost in the clutter. So what can we learn from this? You may recall that a study was carried out some years ago on the future of Raycons to indicate the options available. And one of those options was the modification of existing Raycons. That was expected to be a fairly low-cost option. Another one was to produce a new technology Raycon to match the new technology radars, obviously a much higher option with significant development costs. A third option was to do away with Raycons altogether and replace them with some other technology. And this was mentioned yesterday, I think, as AIS being a potential replacement. That's not a straightforward choice, although AIS is generally cheaper than Raycon. It does rely on GNSS, in particular GPS at the moment, and as discussed this morning, there's a potential vulnerability there. And you're also putting all your eggs in one basket. You're relying on GPS for your positioning and for your aids to navigation. So Raycon's radar-based do give you a separate system, independent system. So the recommendation from this trial, at least, on the basis of this trials with this particular NT radar, would indicate that modification of existing Raycons to improve their response should be considered, obviously in consultation with Raycon manufacturers. Those modifications could include increasing the receiver sensitivity, removing the scalable response, which seemed to confuse the returns, and possibly designing the Raycom to detect and respond differently to NT radar. But that's not something we've investigated at this stage. Another lesson that was learned from these trials was that the differences in Raycom performance were quite considerable, and this may indicate that better standardization of Raycons should be considered. And that might indicate that IALA should review the Raycon standards and see whether they need to be improved, tightened up. And so, in conclusion, I would say that IALA is invited to consider the results of these trials when it next discusses the strategy for the future of Raycons. I'd like to thank the captain and crew of the CIL Tender Granuel for their great cooperation with these trials, and also the organisation provided by CIL's Marine and Engineering departments, and for the participation in the first trial of Laurie Barker and Peter Douglas, and the radar manufacturers under our consultant, Professor Andy Norris. That concludes my presentation. Thank you, Chairman.
Thank you, Nick. I think very interesting and important work you're carrying out there, so thank you for that update. Our next speaker is Jens Pedersen. After graduating in electrical engineering, Jens was employed as a research assistant working with microwave technology and satellite-based radar at Queen's University in Kingston in Canada. He is the Director, Product Portfolio and Innovation for Therma Scanter Radar Systems, and is Therma's representative in the IALA VTS Committee. He is a renowned expert within the radar industry and highly respected as a senior advisor to colleagues and customers. He is going to speak to us this afternoon on a new generation, solid state, fully coherent, frequency diversity and time diversity radar with software-defined functionality. Jens, if you please.
Thank you. Ladies and gentlemen, good afternoon. I'm honored to be here at the IALA conference to present the results of a successful project. I'm especially pleased to do it here in Cape Town. This beautiful town played an important role for our VTS activities. Radars for Robben Island and Cape Town was amongst the first Therma VTS radars installed outside Europe. It was a big challenge to handle the wind conditions here, and the experience gained resulted in much better cloud processing, which since then has been beneficial for all VTS radars delivered from us. The background for the development discussed by my paper is large and expensive radars for military applications. In fact, we at Therma made our first coherent solid-state radar back in the 1970s, but for quite a different application. Making it for surveillance has been in our minds for almost as long, but until now, technology did not allow